So today we're going to start discussing the unit on covalent bonding, and today we're going to look at hybridization and the localized electron model. So the localized electron model, we've talked about this before, says a molecule is a collection of atoms bound together by sharing electrons between their orbitals. And if you remember, we were drawing Lewis structures. These represent the arrangement of those valence electrons. Then we use the Vesper model, which predicts the molecular geometry. Okay, so if we look at CH4, which is methane, each hydrogen donates one valence electron. And carbon is going to donate 4 valence electrons. 3 of those are 2p, and 1 of those is from the 2s orbital, because those are its valence electrons. So this creates 2 different types of bonds when we bond hydrogen and carbon together in the methane molecule. We have a 1s to 2p, 1s from the hydrogen and 2p from the carbon, and then we get a 1s to 2s. So we have hydrogen-carbon bond here, and then a 1s, and then since carbon also has a 2s, we have a 1s to 2s bond. Okay, so we've got different types of bonds. But according to molecular geometry, CH4 is tetrahedral, which means it has 4 identical bonds, because all 4 try to be as far apart from each other, which gives it a tetrahedral shape. And so we kind of have to reconcile the fact that we have these different types of bonds with the fact that when we do the geometry, they all appear to be identical. And that's where hybridization comes in. So hybridization is a mixing of native atomic orbitals to form these special orbitals for bonding. Okay, so we're kind of making a hybrid. Oh, look, it's called hybridization. Okay, so for methane, for our CH4, we have what's called sp3 hybridization. Okay, and this is formed from 1 2s and the 3 2p orbitals. So we have a 1s 2s and then 3 1s 2p's. And so we call that sp3 because we're going to make the number of bonds, exponents, I guess. So since a molecule is just the sum of its parts, it always wants to achieve minimum energy, and these hybrid bonds are going to help do that. So whenever a set of equivalent tetrahedral atomic orbitals is required by an atom, then we would assume that that atom adopts a set of these sp3 orbitals. Okay, and so as you can see, here's our single sp3 hybrid orbital, here's the s, and here's the p. Here's a different shape representation, and then when we put it together as our methane or our tetrahedral, we can see that each of these is forming this sp3. Okay, let's look at an example. So we want to describe the bonding in the ammonia molecule using the localized electron model. Okay, well the first step is to draw the Lewis structure. Okay, so ammonia is NH3, and so we know that nitrogen donates 5 valence electrons, each hydrogen donates 1, and so that gives us 8, and so we'll do nitrogen, hydrogen, 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 lone pair. Okay, so that's our Lewis structure. So by now we're going to assume that you know how to draw those. Okay, number 2, or step 2, is to do the valence shell electron pair repulsion geometry. Well, here we have 4 bonding sites, but one of those bonding sites is a lone pair, and so it's going to push everything else out of the way, and that gives us a tetrahedral shape. And because we've got 4 bonding sites. And so now our third step is to do the hybrid orbitals. And so since we have tetrahedral, that means that we are sp3 hybridized. Okay, let's look at, there's lots of other types of hybrid bonds or hybrid orbitals, so let's look at those other types. Okay, so our next example is ethylene, which is C2H4, and if we do the Lewis structure, it has trigonal planar geometry. And so let's see if we're going to have room to do that. So each carbon contributes 1 2s and 3 2p valence electrons, just like we talked about for the methane. And so we now have sp2 hybridization. So we have a 2s and 2 2p orbitals are used. So you might be saying, well, wait, there's 3 2p electrons and only 2 of them are participating in a bond, and so one of them hasn't been used, and so it is perpendicular to the plane of the hybrid orbitals. And so if we draw our ethylene, we end up having a double bond, and so that is going to play a part in our hybridization. And so here's a picture of what we just drew. So here's your hydrogens and then your 2 carbons, and they're calling this a pi orbital, or here it is as the double bond, they're calling it a pi bond. So let's talk about what the difference is between this sigma bond and this pi bond. Okay, so we can have what's called a sigma bond, and it's a covalent bond in which the electron pairs shared in an area centered on a line running between atoms. Think of it like a single bond. Okay, so for C2H4, this is formed using sp2 orbitals on each carbon and a 1s orbital on the hydrogen, because remember, hydrogen contributes 1s valence electrons. A pi bond is a covalent bond in which parallel p orbitals share an electron pair occupying the space above and below the sigma bond, basically. And this pi bonds will only occur in double and triple bonds. You won't have one in a single bond. A double bond will always consist of 1 sigma bond and then 1 pi bond. And so a triple bond will consist of 1 sigma bond and 2 pi bonds. So you're always going to have a pi bond. Or sorry, excuse me, you're always going to have a sigma bond. So whenever an atom is surrounded by 3 effective pairs, so trigonal planar arrangement would be an example of that, a set of sp2 hybrid orbitals is required. Ethylene has 3 effective pairs around each of those carbons, and so it is sp2 hybridized. Okay, let's look at sp hybridization. So for example, let's look at carbon dioxide, which is linear. Carbon contributes, same thing that contributed for all the other examples, a 2s and 3 2p valence electrons. But each carbon, or I guess our 1 carbon, only has 2 bonding sites, and so we would call that sp hybridization, because 1s and 1 p orbital are participating in that bond. And so we have, whenever there are 2 effective pairs around an atom, it will always be sp hybridized. We have 2 2p orbitals that aren't used, and so these are going to create pi bonds with the oxygen. And let's see. So the sp will form sigma bonds, and then the O has sp2 orbitals because of its trigonal planar arrangement. So let's look at a drawing of this. So we have oxygen. So first, if we did our Lewis structure, okay, we'd have some lone pairs around our oxygens and then our carbon. This is a linear arrangement. Okay, so now if we do the hybridization, we have our carbon, and we kind of draw them as teardrop shaped. So because we have 2 effective pairs or 2 bonding sites on the carbon, we say that that is sp. So sp hybridized. Now if we look at each oxygen, we've got 1, 2, 3 bonding sites. Well, if you remember from our previous example, 3 bonding sites was sp2. And so if here's our oxygen, we've got an sp2, and then here's a lone pair, and here's a lone pair. Oh, that's so small. And then if we do our other oxygen, it's the same deal. So here's our sp, and I'm just going to label it here because I made that too small, sp2. And then we've got 1 lone pair and a second lone pair. I don't know why I keep writing it 2. Okay, sp2. And so we're looking at kind of each atom individually at the number of bonding sites, but we're going to base it on the central atom. And so here you can kind of see what we just drew. So here's our carbon and oxygen. This is forming our sigma bond. Okay, and then we've got 1 from our oxygen and 1 from our carbon participating in a pi bond. And then we've got our other double bond on the other side here. Okay, let's keep moving on. So we have acetylene, which is C2H2. It is actually triple bonded. Okay, and so the triple bond is going to count as 1 repulsive unit, so 1 bonding site. So each carbon in this example is similar to CO2 in that it has 2 bonding sites. And so each carbon has 2 effective pairs, and so we say that that's linear, and so it is sp hybridized. And so this leaves those 2 unchanged p orbitals, and so those are going to combine into our pi bonds for the triple bond. So for each carbon, we have one sp forms a sigma bond with the hydrogen, and then one sp forms the sigma bond with the other carbon, because we have 2 carbons bonded together. And then the 2 pi bonds are formed from the overlap of the 2 p orbitals on each carbon atom. And so if we drew this, so we basically have our hydrogen bonded with a carbon, triple bonded, and so we've got our sigma bond and then our 2 pi bonds. Okay, let's look at another example. So let's describe the bonding in the N2 molecule. So step 1, draw the Lewis structure. Each nitrogen donates 5, so that should be 10 valence electrons. And if you do the Lewis structure, 10, it should come out with a triple bond. So this is a linear geometry, and so now we want to draw the hybridization. Well, each nitrogen, and there's only nitrogens in this molecule, it has 2 effective pairs, and so we would say that it's sp hybridized. And so here's our N, and maybe I can draw this one a little better, sp, and then here's our other N, and there. So this is our sigma bond, okay, and then we've got a lone pair, and a lone pair, and then basically we're going to take those p orbitals and connect them to form our pi bonds. And so that's how we're going to get a triple bond. Okay, so we've looked at sp3, sp2, sp. Now what about those exceptions to the octet rule where you have more than 4 bonding sites? So PCl5 exceeds the octet rule. Its geometry is trigonal bipyramidal, and that's because it has 5 bonding sites or 5 electron pairs. So anytime you have something with 5 bonding sites, this is DSP3 hybridized. And so that's basically what this says. A set of 5 effective pairs around a given atom always requires trigonal bipyramidal arrangement, and that means we have DSP3 hybridization of that atom. So for chlorine, each of those chlorines in the PCl5 is surrounded by 4 electron pairs. So for each chlorine, it is tetrahedral shaped, and we would call that sp3 hybridized. For the 5 P to Cl, those are sigma bonds, and those are formed by sharing electrons between the DSP3 hybridization on the phosphorus and the sp3 hybridized on the chlorine. And then on the chlorines, the other sp3 orbitals will hold lone pairs. So if we look at a picture of this, let's see, where can I fit it? Maybe right here. So we've got phosphorus, and then okay, so each let's start from here. Let's do Lewis structure first. That's going to be our first step. So chlorine, 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 and chlorine. Okay, and then we know each of these chlorines has 3 lone pairs. Okay, so that means 4 bonding sites on each chlorine, 5 bonding sites on the phosphorus. So now if we head down here, 5 bonding sites is DSP3. So DSP3, and then each of our chlorines is sp3 hybridized because it has those lone pairs. So then we would do another chlorine as sp3, that's our lone pair. Here's another lone pair, and here's another lone pair. And then we would keep going for each chlorine that's bonded to the phosphorus. So for another chlorine, we'd have DSP3, and then put our chlorine over here with the 4 sp3 bonds, and we could do that for each of the 5 chlorines that's bonded around the phosphorus. Okay, so we want to describe the bonding in the triiodide ion, which is I3-. Well, iodine donates 7, so that's 7 times 3 plus the 1 from the ion, so this gives us 22. So first let's draw the Lewis structure. I, lone pair, lone pair, lone pair. Okay, now if everything is stable or has 8 or obeys the octet rule, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. But we know this is an exception, so we're going to add, another electron pair. So let's look at that central atom. The central iodine has 5 bonding sites, and so it is DSP3 hybridized. Now each of those outside iodines has 1, 2, 3, 4 bonding sites, And so these are all sp3 hybridized. Overall, this geometry we would say is linear because it's just those electron pairs that are around. So if we wanted to draw the hybridization, here's our iodine. Okay, we've got, let's see, one bonded, so that's our DSP3, and then here's one of our outside iodines. Because it has 4 bonding sites, that's sp3, and then it's got 3 lone pairs. And because that's 4 bonding sites around the outside iodine, they're all sp3. And so then this iodine is got our exception to the octet rule. So each of these lone pairs is DSP3 hybridized. So here's our other one. And then here's one on the bottom. And then it is also bonded to another iodine. So there's our bond. And then here's our other outside iodine. And that's got 4 bonding sites on it. So that is sp3 hybridized. So that's the bond. And then here's our lone pair, and lone pair. Okay, so we're kind of looking at each atom individually, but then overall, because it's based on the central atom, this is DSP3 hybridized. Okay, so we can have 5 bonding pairs or bonding sites around a central atom, but sometimes we can also have 6. And so that leads us to D2SP3 hybridized. Okay, so if we look at sulfur hexafluoride, SF6, it has 6 electron pairs around the central atom, giving it an octahedral geometry. And so this is D2SP3 hybridized. So anytime there are 6 electron pairs around an atom, they're arranged octahedrally, and it is D2SP3 hybridized. The fluorines that are around the sulfur are going to each have 4 bonding sites, and so they would be sp3 hybridized. And then each of the D2sp3 orbitals on the S, or on the sulfur, because it has 6 bonding sites, are going to bond with the sp3 orbitals on the fluorine. And then the other sp3 orbitals on the fluorine will hold lone pairs. So let's look at an example of that, because this gets kind of crazy. Okay, so how is the xenon atom in XeF4 hybridized? Okay, well, xenon donates 8 valence electrons. Each fluorine donates 7. And so that comes out to a total of, what, 36 valence electrons? I did my math right. So let's do the Lewis structure first. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, and 36. So now we've got another exception. We have 6 total bonding sites around the xenon. So that means it's D2sp3 hybridized, octahedral arrangement. So if we wanted to draw this, here's our xenon. So let's see. We've got D2sp3, and then here's one of our fluorines. And because each fluorine has 4 bonding sites, I should draw these bigger, it is sp3 hybridized. And so we'll just do one of the fluorines because they are all going to be the same, and there's really no sense in drawing that gigantic, crazy looking thing. And so then we've got another D2sp3, okay, and that's going to go to a fluorine, which is going to look exactly like this one. And then we've got another bond to the fluorine over here, and then a 4th one, D2sp3, and then we've got 2 lone pairs, so here's one, and here's another one. Okay, and each of these fluorines is going to look just like that one. Okay, so let's kind of just review real quick. So to describe a molecule using the localized electron model, you need to draw the Lewis structure. Then you need to determine the arrangement of electron pairs using molecular geometry or VSEPR, and then you specify the hybrid orbitals needed to accommodate all those electron pairs. Okay, so based on the number of effective pairs that you have, here's your general geometry, and then here's the hybridization. And so you can think about it based on where the valence electrons are and what element they're being contributed from, and that's going to coordinate to either D, S, or P, which should help you figure these out. So number of effective pairs related to geometry related to hybridization. This is going to be important to know. Okay, so what I'd like you to do is go through and try these, and then we will do them together in class and just kind of review, make sure you know what's going on.